Hello everyone. Welcome to this year's Career Development Program. This event is organized by the IEEE Monash Student Branch. As most of you know, IEEE is a professional organization with more than 400,000 members with the stated goal of advance technological innovation. So here at Monash ECSC department, we're part of IEEE as a student branch, and our purpose is to organize events for the benefit of students and to facilitate networking. Just to name a few examples of the events that we've had and the events that we will have in the future. We have workshops, the Altium workshop we had last month as an example, and we'll have a C++ workshop coming soon. We have excursions. We visited Channel 9 last year, and this year we plan to visit Big Roads. We have social events. We had a pizza event for our new postgraduate students to welcome them to the department, and we'll have a sporting event for students and staff later in the year. So to find out more about us and the upcoming events, please visit our website or like our Facebook page. About the CDP, this is the second year that we're organizing the Career Development Program. After today's event, which I'll talk about shortly, tomorrow from 1:30 to 3 p.m. we have, there is a technical recruitment advice session presented by a consultant from Monash Careers. Tuesday next week we'll have the industry panel session with 3 guests from industry, Mr. Ray Keefe from Successful Endeavors, Mr. Hung from Ericsson, and Mr. Peter Munstock from Minifab. And finally on Thursday, June 5th, we have a success story session where we have invited 3 successful Monash alumni to speak about their career paths after they graduated from Monash as postgraduate students. For today, we have Professor Emanuele Viterbo to speak about a career in academia and academic life in general and his experience. Professor Viterbo received his PhD in electrical engineering from Politecnico di Torino in 1995. Between 1995 and 1997, he held a postdoctoral position in Politecnico. He then moved to USA as a research fellow at AT&T Research Labs. In 1998, he became assistant professor at Politecnico, and then in 2006, a full professor at the University of Calabria, Italy. Professor Viterbo is a fellow of the IEEE. He is a highly cited researcher, and he is also a member of the Board of Governors of the IEEE Information Theory Society. He has received numerous awards and honors for his research and service. He came to Monash in 2010 as a professor of electrical engineering and the associate dean of research training of Faculty of Engineering. Professor Viterbo, thank you for accepting our invitation. I'm sure everyone's looking forward to your presentation.
Thank you. Thank you for the invitation. And good work about organizing all this. It's very useful. So, when last night I was thinking about the title to put on my slides, which I didn't prepare last night, I noticed that there was a difference of 25 years between my graduation as a master's in electrical engineering and today. So that's how the Silver Jubilee came out. But otherwise I didn't know what title I should really put, but that was my best guess. So let me first introduce myself. You already gave away half of my slides, no. But almost there. So I had some early interests in telecommunications, and you see I was working already with wireless. There's no cable here coming out, and that was 1970. I had to date that somehow. And then here is more or less my trajectory over the globe. So After I graduated in '89, I worked from '90 to '92 as a patent examiner in the European Patent Office in The Hague. And that was a kind of research job. It's like, I would call that a passive research job, because you read about other people's ideas and patents, or they write in the patents. So in a way, I did 2 years of literature review, and you can think of it in that way. But in an area which was slightly away from my study, so when I studied as undergraduate and master's student, I did my work in electromagnetics, and then when I went to the patent office, I started looking at coding and modulation. So I had taken the courses in that, but it wasn't my main interest at that time. But then I kind of read for 2 years basically all the literature on coding and modulation that appeared in that period. And that's because then the work there was get a patent application, read it, and then go into these huge shelves where you had piles of old patents and papers, and you would just flip the pages and look for something similar. So there was no Google at that time, and there was a little bit of InSpec and Scopus databases available, and some patent search, which really was relying only on the keywords and the abstracts. So it was very limited online search. It was handmade Google there. So I did that for a couple of years, and that was kind of, on one side, frustrating because you would see nice things, but then you didn't really do them. You would just read about ideas and solutions. Then you learned the background, but there was no active activity in there on that side. So then I decided to go back to do my PhD, and then so I did that. I took a PhD in telecommunications. Started in '92 and then ended in '95, and that's where I worked mostly on coding and modulation for wireless channels. Then in '95, after I finished my PhD, that's a critical moment in your career in general. You don't know if you're going to go to industry or try to go on with academia. And so I was, for 2 years, postdoc still in Torino, where I did my PhD. Then I had this opportunity of a postdoc in US, and so I did 1 year at AT&T Shannon Labs, and that was very, very interesting because it was the time where the MIMO started becoming popular, and there were some of basically the key people who introduced MIMO, and we started from AT&T. So the people like Tarok, who had just worked with Alamuti, was there, or Calderbank. So these were the big names in MIMO in that time. So that was very interesting experience. As well, there were two kinds of people in this Shannon Labs, which was the lab which was split off from the Bell Labs once AT&T gave away Bell Labs to, I think, Alcatel, to Lucent at that time. So in the Shannon Labs there was a department of mathematicians and telecommunications engineers together. So it was very, very interesting mix there to listen to talks of really bright people there. Then, so after 3 years of postdoc, that was very long time, if you think, after my PhD, I was trying to get a job as researcher or as an assistant professor, and finally I succeeded in '98, and so I must say that was gave myself the last chance. This was my last chance. Either I get a job in academia there, or that's over. But it worked. So luckily I was successful at that point. So I started as a research assistant professor, and then that's when you start doing some teaching, and that's a new thing when you move from research only to teaching. So maybe you have some experience in doing some teaching as a PhD student, or assistant in teaching, but then this is when you really have to do it all by yourself, and that's another key point. You must see if you still like it. Okay, and I liked it still, and so I went on. In 2005 I got associate professor, and then at that point becoming full professor in Polytechnical was probably very hard, because there was a very large group there and very strong candidates, much older than me. So that was the moment I decided I would try my luck somewhere else to become professor. So I moved from A to B to C to D, and then back to B again, and then from B to D. Okay, so, and that's university in South Italy. So and that's where again you change your career in terms of the things you have to do as professor compared to what you had to do as researcher. You have to have a group, leads a group of people, have manage a lab, and so on. So this is another step in academic career, I would say. Then and then in 2010 I got the offer to go to point E, which is here. So I had upside down at that time, but today is this way, so it's straight up. Okay. So, and I don't think there is any space to go further to Antarctica, to further south than that. That's it. Okay, so here in Monash, have started the software-defined communication lab, which is down in building 35, and this was a celebration of Sphere Decoder. So, what is Sphere Decoder? So, well, it's basically my most cited work. So that's, I wanted to tell you a few things about this result as just a sample of research, I think, that happened to attract the interest of many people. So I want to give you this short technical bit of presentation. Somebody already has heard this in the audience, but just bear with me for a little bit of technical talk. Then we will go back to discussing about quality of research and other things. Okay, so Sphere Decoder, what does it solve? It actually solves a minimization problem where you have a given function with n variables, and but the problem is that the variables are discrete. So you have normally a finite and a set of discrete values for these variables. Imagine they can only be some integers. And if you want to minimize given this function, well, there is one way to just exhaustively test all the patterns for the variables. So the total number will be this exponential in n. Okay, in some cases this is not that hard, and in fact if the function f has a simple form such as it's the sum of many functions, each function individually is a function of one of the variables, then this is quite easy because you essentially do it in one dimension, each one. So you minimize each one of the terms, and then it will be simple. There are other functions which are quite easy to minimize, given the discrete nature of the variables. And these are the functions where they can be written as a sum of functions which are of pairs of interconnected pairs. So 1 and 2, 2 and 3, 3 and 4, and so on. So if you can write that sum as, if you write the function as sum of these functions which depend on pairs, there is another famous algorithm which solves this problem of finding the minimum of this function. And it's the Viterbo algorithm. Okay. Now, here comes the sphere decoder, and this is another case where something this minimization problem can be solved with in a simple way, well, relatively simple way. So what's the shape of the function you want to minimize? It has to be a sum of a number of functions, each one depending on the first one on one variable, the second one on the two variables, and then three variables, and so on. So you have increasingly more variables into the terms. The extra assumption we need, and I think you needed it also in the previous case, is that these functions must be all positive values. So they must be positive. Okay, so how do you try to solve this problem? Well, first of all, you use a tree representation of the problem, just to see how many trials you should do. For example, if you have three possible values for the variables, you could draw this tree where you have at level here you have x3 and you have three possible values. These are 0, +1, -1, and at each node you will have three choices, which are the variable. And then if you look at the path from the root to a leaf, you will get a total of 27 paths down the tree, and these are all the possible combinations of the variables that I need to test. So let's see this extremely simple example where we just have two variables. So the first function is f2 of x2, and the second function is f1 and 2 of x1 and x2. What I have now, the variables here, I assume they can take four possible values. I don't care what the values are. What I draw here is the value of these two functions, f2 and f1, 2. So here I have the f2 on this branch is 1, f2 on this branch is 3, 2 and 4, and so on. And then on the second branch, I will have just the values on here, the values of the second term, this one. So when I want to compute the sum of these, I just take a path down the tree and I add the values on the branches. So down here I get to 2, 1 plus 3 is 4, 1 plus 4 is 5, and so on. 3 plus 1 is 4, and I can do this exhaustively. I have computed all the possible values of the function, and I just need to find the smallest one. Here it is. That's exhaustive search. It cost me 16 computations. So let's do it instead by sphere decoding. Okay? So the approach is the following. We take a greedy approach. We start from the first level, and we see that this way you get 1, 3, 2, and 4. So we go down the path which is the least here, and then we go further down that path and we explore the smallest here and among the remaining ones. So I do 1 plus 1, 2, plus 3, 4, 5, and 6. I choose the smallest one just within these 4 down here. Now that I found these 2 here, what I can do is that if I go back and start another path down here, first of all I find 3, but 3 is much bigger than the value I found before. So it's already, you can discard that. Again, here I have 2, which is also beyond 2, which I already had. It means if I went on, I would just add things, so it wouldn't do any use to find the smaller one down here. And also here, I already reached 4, it can only increase, so it's not worth going down this path. So in a way, I minimize partial sum by looking at the first level, and then I go down, I find the total sum, which is my first guess, and I use this as a bounding value to stop from going down other paths which are not going to bring any smaller value anyway. Okay, so this is the sphere decoding as people more easily understand it today. And see, it's a tree search algorithm, and that's the way you can think of it in possibly the simplest way to explain it. Okay. So I didn't get to this explanation when I looked at that. So well, I actually started from the application, and the application that I had in mind was the following. I have a communications channel. I need to transmit a signal, goes through a certain channel which adds some noise. It's received, the signal is received, and you want to find the most likely, how do you guess what signal was transmitted? So you have to find the most likely transmitted signal. So this problem, you can model your signals as points in a Euclidean space, so as vectors in Euclidean space, in particular as in a regular grid, which is called a lattice. You can pick one of these points as your signal, transmit that one, and you will get a y a receive point which is not on the original grid, because the channel has introduced some distortion and the noise, there has been added noise, so you get this start point which is not related to what you transmitted. So what's the best thing that the receiver can do is to look around the y point, the received point, and find for the closest point to that one. Now the distortion of this grid is due to the channel, and the fact that the point is not on any of the distorted points is due to the fact that there is additive noise. So the general model that you have for the channel is in a vector model. You transmit a vector x multiplied by some channel matrix H. You add a noise vector, and you receive y vector. Now the problem, as I said, to find the most likely transmitted signal is equivalent to finding the closest point y to the grid on the right. So this is this problem. Okay, it's an NP-hard problem, because you would have to search all the points, and it's exponentially increasing with dimension. So it's a typical problem in demodulation and many other applications where you have this vector model. So how did I get to that? So let's go back and see where I came in and look at the history of this algorithm. Okay, so in fact this algorithm was hidden in a way in this paper by a mathematician called Michael Post, who published in '81, and he had this problem about finding shortest vectors in lattices. And he gave this algorithm, which is not finding the closest vector, it's finding the shortest vector. So it's almost there. So I just played with the fact that I was looking for the shortest vector in a shifted lattice. And then I modified that, the algorithm as it's presented here, and made it into the decoder I was looking for. Now, this code actually has a geometric interpretation which I put in my, my first paper I published in a conference in '93. That was 1 year after I started the PhD. And that was first conference, very scary to go and give the talk. It was in France, so they wanted the French abstract as well, so I needed some help in getting that translated in French. This is my supervisor, it's Ubilieri. So this is where, in this paper, I gave this geometric interpretation, and that's where the name sphere decoder then came from. So this picture is funny because it has on the other side of my supervisor, Viterbo, who was the Viterbo decoder guy, and he just wanted a picture between two Viterbis in general. So that's how that picture came. But so the geometric interpretation of that algorithm, I think, was that instead of searching in a sphere for all the points inside the sphere, you would search in an arbitrary grid, you would search inside an ellipse for the points with integer coordinates. And this interpretation was more easy to understand, at least geometrically. Okay, that was '93. In '94, I found, well, actually much later, I found this paper that somebody else had also found post paper from '81 and used it for another case, another application. I wanted to decode some ternary Golay codes, and so I came to the lattice world and so on. But this guy also noticed that he had a similar problem, and he got back to the post paper and used it as well. I met him long time after, and we discussed how we found the same paper, very old paper, hard to find, and it was referenced, so it was not hard to find. It was actually hard to find a paper copy of it because, again, no Google and not available. So I had to get it posted from libraries abroad. Then that paper from '93 basically was, I didn't think about it was so interesting until I met Joseph Boutros from ENST Paris, who was working with other lattices and lattice constellations. So again, it was useful to decode his lattice constellation codes. And that's when we wrote this paper together, which was an application of the basic lattice decoder to these fading channels. And then this was the very successful paper because basically it gave you the tools to write your decoder. So you can see there was a flowchart, and from flowchart to code, it's really easy. There was straightforward explanation and implementation of the code. So I think that's one reason why people kind of cited this paper, because they found a good reference how to implement it, and they could do it immediately. Then after that, many papers, so who was interested? Well, anybody who had a problem which was set into that form y = hx plus noise, which is a very standard model we find in many applications. So you find then here a long sequence of papers. I'm just highlighting some first papers in each area where it was applied. That was the first patent, some VLSI implementation, and complexity analysis and other things. And sphere decoder and sphere decoding got, if you Google it, and you find 40,000 hits on this word. So the name sphere decoder, I didn't give that name. It just came to be popular maybe a bit later, and now it's known as sphere decoder. So the conclusion of this part is that I think, summarizes in this sentence. So, chi cerca trova, chi ricerca ritrova. Which means if you search, you find. If you research, you refine. Okay? So it was there, you need to refine it. But I would add and make it maybe useful to solve your problem. So many solutions are out there. You maybe need to adapt them to your problem to make them useful to solve your problem. Okay. So that was all about sphere decoding. I won't bore you further on this. So I then would like to share with you some quotes from a very nice talk given by Richard Hamming, the guy of the Hamming Codes, in 1986. And the title of his talk was You and Your Research. And there are some quite funny and interesting ideas in there. And you can find it online. You just Google You and Your Research and you'll find this, the whole speech transcript. And but I collected a few of these sentences because maybe you would like to think them over. They can make sense or not, but we can discuss about them if you like. So yeah, this was you say to yourself, yes, I would like to do first-class work, or society frowns on people who set out to do really good work, but you should say to yourself, yes, I would like to do something significant. So you may have this question during all your PhD. So I had this question all the time. Am I doing something significant, useful? I don't know, okay? I still didn't know. So I did something. I didn't know it was significant. You see, it was in '93. I didn't believe it was significant at that time. I had no idea. And then it turned out to be useful. So, I don't know. This sentence from Hamming, maybe it doesn't fit my case. I was not believing it was significant. That paper, I did other things which I believe were much more interesting to me. And then it turned out that this was more interesting to other people than myself. So having a bird's eye view is hard when you're digging into it. So if you can sometimes take the time to look at things from further away, it may help to understand if what you're doing is significant. Okay, this is another one. Once you get the courage up and believe that you can do important things, then you can. If you think you can't, almost surely you're not going to. Great scientists will go forward under incredible circumstances. They think and continue to think. Again, Hamming was really a bold guy, so I don't really agree with that, but you may agree. Okay? It's just thought-provoking quotes. This one, it is a poor workman who blames his tools. The good man gets on with the job given what he's got and gets the best answer he can. So maybe that's true. You can find that when you don't have all the tools, you will have a smart idea to get around it. And that could be true. This is about working hard, I would say. Knowledge and productivity are like compound interest. Given two people with exactly the same ability, the one person who manages day in and day out to get in one more hour of thinking will tremendously be more productive over a lifetime. So, yes, dedication definitely probably is rewarding in terms of successful outcomes. So, where to look for significant results, significant research? Well, Hamming actually had the fortune to work with great physicists in Los Alamos. He was a manager of the computer system, and at that time, using computer was a very difficult thing to do. They need to have you need to go to a specialist, which was the computer manager, which was Hamming, and present your problem, and then he would code the computer, maybe in binary even. So, he had the fortune to talk to many really great physicists and think about what was great science and what are the great questions to be answered. So I think he found this point that when you find apparent flaws, you've got to be sensitive and keep track of those things. So when you see something that's probably not right, that's probably a good place to look into more, because then things that cannot be explained by your theory, by the theory then means that the theory is not fit, and maybe there is more things to do. So that's often where scientific contributions appear. Okay, it's that simple. If you want to do great work, you clearly must work on important problems. Okay? I finally adopted what I call the great thoughts time. So when I went to lunch on Friday noon, I would only discuss great thoughts after that. By great thoughts, I mean ones like, what will be the impact of computers on science and how can I change it? So it's very abstract thoughts. But just having this conversation on more higher level topics gives you a better picture where you are and what you're doing and how significant it can be. Okay, self-manage. So the way to manage yourself is that when you have a really important problem, you don't let anything else get the center of your attention. You keep your thoughts on the problem, keep your subconscious starved, so it has to work on your problem. So you can sleep peacefully and get the answer in the morning for free. So that's kind of ideal. But sometimes, keeping your problem in the back of your mind may help to solve it. In the right moment, you find the solution. Okay, there is a pretty good correlation between those who work with the doors open and those who ultimately do important things. Although people who work with doors closed often work harder, somehow they seem to work on slightly the wrong thing. Not much, but enough that they miss fame. Okay, again, his opinion, but it's more like a metaphor. Doors open, door closed. It means talk to people. The more people you get to interact with and talk to, the more ideas will flow into your mind and maybe back to the people you're talking to. And again, about people you will meet, when you talk to other people, you want to get rid of those sound absorbers who are nice people but merely say, oh yes, and to find those who will stimulate you right back. So anybody with hard questions for you, make you think, that's a good thing to have. Okay? So look for them. Okay, so that was just some quotes from the whole talk. It's really nice to read it, and I suggest you read that one, you read the whole talk. And then more about research. This is from a research project which studied research. It's a project in the UK, and they kind of distilled, they interviewed many researchers. So the Hamming were his personal ideas, which right or wrong, but this is more like scientific research on interviews to many researchers. So let's say it's more a systematic approach to pinpointing the interesting characteristics of good researchers, or at least on average, so because this is the result of statistics. So I don't really know if it's good to work with the averages here or not, but these were some of the outcomes of this research. So they effectively divided the skills of good researchers into four major blocks. So knowledge and intellectual abilities, personal effectiveness, okay, engagement, influence and impact, and research governance and organization. Okay, I'll stick to the first two, which probably are more relevant to PhD work, and you can go on the website and read more about the others. But I think it's interesting to look at the list of knowledge and intellectual abilities that were highlighted there. So you have here some cognitive abilities: analyzing, synthesizing, critical thinking, evaluating, problem solving. So these are cognitive. Then you have creativity. So you have to have, well, you don't have to. You may stimulate your inquiring mind, have intellectual insight, innovation, innovative thinking, make good arguments, and take some intellectual risk in your arguments. So sometimes by thinking out loud, you discuss, you realize what's right and what's wrong. And don't be afraid to ask the wrong questions. Okay? There is probably no wrong question, just wrong answers. Personal qualities, again, enthusiasm, perseverance, integrity, self-confidence, self-reflection, responsibility. Things that you may think by yourself, or, you know, it's not the kind of thing you go there and say, I got that, got that, got that. It doesn't really help. Just to know that these were the most popular answers probably they got in their interviews. Self-management, definitely useful. So preparation, prioritization, commitment, time management. You want to really manage well your time. Responsiveness to change. This is really important because, as you may have experienced, your research goes up and down. You know, you have some moment of success, but you will have many moments of non-success. Okay, so there is a lot to learn from those in terms of what you can fix, what you can correct, and if you found something didn't work, it's not all that bad. You know, maybe you can stop somebody else from doing it. So that's also a good result. Work-life balance could be hard. Okay. That's all I had to talk to you about, and I would be happy to have any questions.
Okay, questions?
Do you leave your door open or closed?
It depends who is inside. As associate dean, I leave it closed. As a researcher, I leave it open. Yeah.
Just a quick question. So you said earlier, you mentioned that you have to start teaching now as like an associate professor and professor level. So how much time would you dedicate to your teaching responsibilities and how much to your actual research?
So the best thing is when you can match the two things, when you can really teach the topic that you are closest to. That's really the best, because you can give the best to your teaching in that way. When you are teaching some other course slightly away, it will take up more of your time, but very often it's rewarding because you get perspective on maybe a side area that you never went in depth, and it's an opportunity to learn something on the side which could be still useful for your research.
Okay.
Even if it's basic year one, there is still some interesting tricks that you may learn from there. Yeah. In terms of time, yeah, it's
it takes what it takes.
It takes what it takes. Yeah.
Yep.
If you know it, if you don't know it, it takes more.
Okay.
If you have to prepare all the material, it takes a long time.
Mm-hmm.
So I would say one experience that I definitely can say is after the third year you teach one course, it's perfect. Okay, so first year is not so good, second year almost fine, third year is okay. I mean, it won't improve much more. And then probably after a few more years, you better change subject.
Yep.
To change, just to refresh. But it requires a bit of effort to start a new subject completely.
Yep.
So that's.
Any more questions?
Yes.
Question. From the department point of view, what is the more, how can I say, priority to select an academic to be employed, to have more skills on the teaching or to have more skills on the research? Or none of them?
No. I think most interviews I had were focused on research. So usually it's focused on research, but in Italy I did an interview for many assistant professor jobs before getting the one in '98. So there they do have an interview which is actually a lecture you have to give. As you get a title of a lecture, and then 24 hours later you have to give this lecture, and they will evaluate you on that. But in other interviews, you will have generally a technical talk during your interview, so it's not always directly related to a lecture. So yeah, it depends where. But in I think your research will play the biggest part in your chances. Yeah. Yes.
So when you graduate from your PhD and you tried your luck to determine you go to the industry or stay in the university, and you said you tried luck by applying for an assistant professor. And did you have the preference for staying in the university or going to?
Yeah, I did have the preference. So, and I think I did work 2 years in the patent office, which was neither industry nor academic. It was a strange place, I must say. It was uniquely strange place in terms of working experience. Okay, I did that, so I even didn't have to do my military service in Italy, so there were other motivations to do it. But apart from that, it was compulsory just up to a few years after I went through. But it was in the end very, very useful to work there, and having. So I did see what it was not academic. Then I did see some industry environment, because I did some consulting on patents during my PhD. So I did see some industry work there. I did have that experience of what was going on in industry as industry job. I did some interviews at that time for industry, and it was always as backup. I did still want to continue the research. Yeah, I did enjoy that the most.
What aspects of the industry work that you dislike?
I don't know really. I think it was the fact that you focus on a very narrow problem. It's extremely narrow, maybe in big depth, but very narrow. And in your research, although you do one narrow problem, but you can do many of them. You can do many problems in parallel at once, and you can do more things, and you have a slightly more general point of view than once you are stuck inside one stream in one company. That was my preference, to have the broader view that you will struggle to get when you go straight into a company, because then you will be working in one specific line of work. And then of course it's up to you to to update yourself and so on, but I don't think you will have that chance any longer, whereas you still have it in academia. And as well as, and teaching is the other completely different thing you will never find in industry. So being able to teach what you know is interesting. Yeah.
Can I add something to your answer?
Sure.
As an R&D engineer,
Yes.
I don't agree with you.
Okay.
They need more insight into different fields.
Mm-hmm.
But as a regular engineer, yes, what you said is true.
Mm-hmm. Yeah.
And
It's
in-
as
in
R&D.
R&D as
Yeah,
an
no.
R&D
In fact,
engineer,
you're right.
as
You're
a
right.
research and development engineer, after getting your PhD or your master's degree,
Mm-hmm.
which is not very frequently
Mhm.
available in Australia,
Yeah.
unfortunately, but in US and Europe,
Yeah.
you need much more insight into different fields.
Yeah.
Sorry.
No, but it's true. There is this distinction is important, and in fact, I must say, my experience with industry was most of the time with R&D or research side and or research centers and telephone company, but the research centers of the Italian telephone company. So I had, let's say, the best part of it, and that was my first choice as for a job, and that was, I would have been still happy to get a job in that area, but then probably I was not so keen to go into commercial part of the business. I thought I was too bad at it, so I thought let's try and do something I'm better at. Yeah.
Okay, any more questions? Okay, thank you.
Okay.
In the end, we'll have-
Thank you for.
Okay, that's it for today. See you tomorrow, hopefully. 1:30 p.m.